Hello everyone, welcome to k-mer analysis with Python, and in this particular video we are going to estimate the genome size of a Salmonella enterica straight from the raw data. So before we run an assembly, we are going to know what's going to be the genome size generated by the assembler. So the first thing we need to do here, of course, is to download the raw data that we're going to use. It's a very small file, only 100 megabytes, so it just take a few seconds. Then we do the same thing over here for the secondary read pair. Same thing, only 101 megabytes. Then we needed to decompress it. So gzip -d, the reads one, and the read pair. All right, the next thing we need to do is do the k-mer counting from this data. And we have the command over here. So it's basically saying that we're going to count using jellyfish. And we are going to consider, you're going to take a k-mers of size 21. -c means it's going to be in canonical mode. And this is how much space we're going to provide for the algorithm. And we just need to run it. And this particular command is going to take, I don't know, maybe 1 minute or 2 minutes. So I'm going to stop now and forward the video. Okay, now we have the k-mers counted. It generated a new file over here. It's called output.jf from jellyfish. And the next thing we need to do is run the command that's going to take the counted k-mers and generate a list of frequencies. So it's pretty fast in this case. We can now open the file, and the way you can hit it is like this. There are 598 occurrences of k-mers with coverage 10. There are 105 occurrences of k-mers with coverage 18. So this in the beginning over here, this 1 and 2, they are mostly errors from the sequencing machine. And they are actually going to mess up with our plot, but let's see this a little bit later. So now we can start coding. Let's start in the main namespace, and we can get a file name from sys argv in the position 1, and we can open this file as a file handler, and we can get the data as lines, so not read, but read lines. You can also see here that the data is separated by a blank space, and there is a break line for each one of the numbers combination. So we can actually go and clean this data set and say that our entry is going to strip, and the strip is going to remove the break line and also split on the blank space for each entry in data. All right, so this gives us a data set that's looking a little bit better. So if you run this script over here, Python plot, and we give output.histo, we can see that we got everything as a list of lists, which is just the same data from the file. And now we can call main, and we can give as variable, as parameter, the variable data set. And of course, you need to create the main function. And for plotting things here, we need to get the coverage. The coverage is going to be our x-axis. And of course, we don't want strings. You can see here that everything is actually string. So we need to convert it to integer. And the x is the first element from the entry for entry in dataset. And we can do the same thing here for frequency. But now we'll look at the element 1. So taking here, it's 0 and 1, 0 and 1, coverage and frequency. And now we got all the coverage and frequency in separated lists. Then we can actually go and plot it, and we give coverage and frequency. We don't have the function we need to create. Well, of course, there is things called plot, so let's give a better name, make plot. So we created a function here, and we are going to use matplotlib for this one. So matplotlib pyplot as plt, just to get a short version. And then we can create the new plot by making plt.plot. X is going to be coverage, and Y is going to be the frequency. And we can actually go and give the labels. X label is going to be coverage, and plt Y label is going to be frequency. All right, after that we can go and save fig, and we can give it a name genome.png. So if you run our script again, we should get now a plot over here, and we can see our beautiful plots. Most of the things here in the beginning are the errors, and the errors are dominating the plot. So if you actually go and zoom in a little bit, you can see there's a bump here, and this is the thing that we are looking for. This is going to be a Poisson distribution, and we are going to get the estimated genome size by taking the area below the Poisson distribution and dividing it by the peak coverage of the Poisson distribution. But then, of course, this is looking very bad. It's not a plot that we can work with. So we could, in theory, maybe do something like this. Like try to guess where is the boundaries for our Poisson distribution. Let's say it would be between 10 and 200. And then we limit also the frequency between 10 and 200. And if we run the plot again, yes, as you can see, it's looking a lot better now. But then you can do that for every raw data that you get, right? You should not be straight guessing where are the boundaries, where it should start and where it should end. So to fix that, we need to create two new functions. It's going to be detect start and the function detect end. All right, and for detecting the starts and ends, the coverage is irrelevant, but we do need the frequency. Oh, there's a typo here. Detect. So how are we going to detect this? Again, if we look at the plot, we can try to detect when things are increasing here and when things are decreasing here. So we are going to look for a list that is increasing, like this. So this is a list increasing. And we are going to do the same thing for the end, but then we are going to be looking for a decreasing list. All right, so let's first detect the start. So let's have a fallback. It's going to be a start at 0, and then for index in range of the elements in the frequency list, the length of the element in the length of the frequency list, we can iterate and get a test list that's going to be just a small part of the list. We don't need the entire list. So we can say it's starting position index and go to index plus 10. This is just a sliding window. So we're going to be iterating the entire list in chunks of 10. And now for this, we need to test if the list is increasing. For doing that, we can make if again, and then we test if everything in this if is going to be true. And what we're going to test in true is if A is higher than J. For A and J in zip test list, and the test list again, but now ignoring the first element. And this is going to give us our start. So it should be the index position. Then we can break here. We can actually go and print things just to visualize in the terminal after we run the script. And it says start at, and we give our start. I hope this is not much confusion, but well, I guess we can actually give a small explanation here. So if we get a list like 10, 20, 30, 40, 50, and then you take the same list, but now without the first element, and then you zip, you are actually going to iterate in tuples like this. 10 and 20, 20 and 30, 30 and 40, 40 and 50. And then we need to check if I is bigger than J. I just realized that the sign here is actually wrong. We want things that are smaller. Okay, now it's right. So is 10 smaller than 20? Yes, it is, so it's true. 20 is smaller than 30? Yes, it is, so it's true. 30 is smaller than 40? Yes, it is, so it's true. 40 is smaller than 50? Yes, it is, so it's true. The zip will ignore this one because it doesn't have a pair. So everything here is true. So yes, this list is actually increasing. And since we started on an index to get the sliding window, we just return the index position for the frequency where we start doing the checking. And this is going to give us the beginning of the Poisson distribution. So we needed to do something very similar to detect the end. And again, we should get a fallback here. It's just going to be the last element in the list. And then for index in range length for frequency. But now we need to make a countdown. So we are not going from this case, let's say that the list is 100 in length. We are going from 0, 1, 2, 3, 4 until 100. So now we need to do the opposite. So we start at 100 and go decreasing. So this is the structure for doing that with range. So just give a -1, -1 here. And then we can do something similar. We got test list and then the frequency, but now the index is going to start at -10 and go up to index. So if the 100 is the last element, we're going to create the new test list from 90 to 100. And we're going to be sliding to the left until we get the condition that we're going to add right here. That again should be the same thing that we did before, but now with the right order where I is bigger than J. For I and J in zip test lists minus the first element. And if all that goes right, then the end becomes the index that where we start measuring this, and then we can actually go and print just to facilitate a little bit, and we print and we return the end here. Oh, we also needed to return the start here. All right, so let's just double check here. So now we are looking for increase, but from the right side to the left side. So now it actually looks like a decrease from the list point of view. So if we find this going from the right to the left, and we try to compare this with this one over here, like taking out the first element. Is I bigger than j? Yes, it is. Again, yes, it is. Yes, it is. Yes, it is. And 10 over here is going to be ignored because the zip doesn't have a match for it. And then we say, okay, the list is actually, again, increasing. Everything is true. It's increasing from the right side to the left side. And this will be flagged as an end for us. All right, so now that we have the detection for start and end, let's actually give it a try. So we do start equal to detect start, and we provide the frequency, and we do the same thing with end, and detect end for frequency. And now we can limit our plot between those start and end. So let's take a look again on our genome. So this is how we estimated by just guessing random numbers. Now we can run the plot again. And we actually got a suggested start at 23 and a suggested end at 140. And it's looking better. Yes, this is actually a very good Poisson distribution. And I think with this one, we can actually estimate the genome size that are present in this raw data. Of course, these detect functions that we just created here, they're not perfect. I'm pretty sure they can fail in 100 different cases, but at least for learning purpose, it gives us an idea of what to do. All right, so the next thing we need to do is to detect the coverage peak. We can already do that again by guessing, looking at the plot. So I would say 78, 77. It's close to 80 over here. And for getting that, let's create another function. So we are going to call it estimate coverage peak. And for this one, we are going to need to provide the coverage, yes, both coverage and frequency. So we can create the function here. Same idea. So the thing with the highest frequency in our plot should be our peak. So we can say higher frequency, higher frac is going to be equal to max frequency. And then we can say that peak coverage is going to be, now we use the coverage, and we need to get the frequency index for the higher frequency. So it should be frequency index higher frequency, higher frac. All right, coverage. So we can also print things again. Peak coverage. Maybe coverage peak sounds a little bit better. So coverage peak is going to be coverage peak. And we are going to need to return this also, because we're going to use it later for estimating the genome size. But now we have what's supposed to be the coverage peak of our Poisson distribution. So we can actually try and see also, not only in a print, but also in the plot. So we go again to the plot function, and before we save the file, we can add a line, a vertical line under the x-axis, and we say that the x is going to be the coverage peak, and we can also give it a color. Let's say red. We don't have the variable here, so we can also let's use short names here. So coverage peak and cov peak here. Yes. And then We just need also to provide to the make plot frequency the variable that we just got over here. So coverage peak equals to estimate coverage peak, and then we provide it to the plot function. Okay, now we plot it, and it says again, it started at 23, ends at 140, and the coverage peak is at 75. So if you look at our genome again, now we can see there's a nice line over here showing us where is the coverage peak. And this is pretty much what we need to estimate the genome size. So it should be our next step. It can happen right before the plot. So we can have this new function called estimate genome size. And for this one, we are going to need the coverage, also the frequency, and the coverage peak. Same thing that we need to actually make the plot. We don't have the function, we created a function over here. And the first thing we need to do for estimating the genome size is to get the area under the curve. Let's be verbose on this one. And then it should be each one of the elements in coverage multiplied by the elements in frequency. And then we sum up everything. So we can make like a sum, and then we can get coverage elements multiplied by frequency elements for C and F in zip, coverage, and frequency. Okay, this should be the area. And then for the genome size, we should just get a new variable here. Genome size should be area under the curve divided by the coverage peak. This may end up in a float, so let's just force an integer here. And we can also go and plot things again. So on f string, genome size is going to be genome size. I don't think we need to return anything here. We are not going to use this information anymore. So we just needed to call here. And then if we run on the script, we got that it started at 23 and 140, coverage peak 75. And then the genome size is 4,865,016. And this is pretty much 4.8 million base pairs, which is a good number for a Salmonella enterica, the origin of the raw data. I'm pretty sure it's something between 4.7 and 5.1. So if you take this raw data and you run using an assembler like Spades or Esquiza, you are going to get a genome that's pretty much around 4.8. Maybe it's 4.7, maybe it's 4.9. Of course, it doesn't need to be exactly the size, it's just an estimate, but it's going to be very, very close, less than, I don't know, less than 5%, I think, of difference in size, because this particular data has the Poisson format, the Poisson distribution. Of course, not all raw data have this. Sometimes we're going to get bumps over here from different populations inside your isolate, or maybe a bump over here, or maybe the error rate it's a lot longer and get merged in the Poisson distribution over here, like this. And then in those cases, our estimate is going to be a little bit worse. But then again, it's an estimate, and it's a good idea for you to know if you're going to find a genome in the size that we're expecting for the species that we're looking for. This should work flawless for bacteria and for viruses. But then, of course, more complex genomes are not going to have this exact format with a single curve for in a Poisson distribution. I hope you enjoyed this video. If you learned something, consider giving it a like and subscribe to the channel. In the next videos, we are going to explore more variations of data and how they are going to plot. And also, we're going to learn how to replace Jellyfish 2 for k-mer counting with our own version written in Python. See you next time.